Hey guys, this is Avinash here, and my topic for CMPE258 short story presentation is understanding GANs and how to regularize GANs under limited data. So let's hop into the topic. Before going into understanding about regularizing GAN under limited data, what is a GAN? GAN stands for Generative Adversarial Networks. Here, what does the word generative mean? At a high level, a generative models means that you have mapped the probability distribution of the data to itself. Okay, for example, in the case of images, you have the probability of every possible combination of pixel values. This means that you can generate new data points by sampling from the same distribution. So, if I am, for example, in a computer vision domain, I can create a model that can create new images from scratch. What does an adversarial mean? It is called adversarial because the problem is structured in such a way that two entities are competing against one another, and both of these entities are machine learning models. So in a GAN, there are basically two components, a generator and a discriminator, which are competing against each other. So thus the word adversarial come here into the picture. Network, since we are using neural networks to train GANs, so thus the word GAN stand for generative adversarial networks. As I said earlier, there are two main important components of GAN. One is the generator and another is the discriminator. So basically both of them are two separate neural networks. The generator learns to generate the fake images, so it can be thought as a forger or something that creates images that looks real to fool the discriminator. The discriminator is some kind of an investigator who learns to distinguish between what's real and what's fake. So these are the two rules of generator and discriminator. So here is the high level architecture diagram of a GAN. So here the generator learns to generate fake images that looks real to fool the discriminator. The discriminator learns to distinguish between what's real and what's fake. Okay, so at the beginning of the game, generator actually isn't very sophisticated, so it doesn't know how to produce real images. So it can be thought as a person who doesn't know how to generate new images. Similarly, at the initial stage, discriminator also know what's real and what's fake, so it won't be able to distinguish correctly. So to start the training of the discriminator using a real data, so that it can be able to distinguish and decide what's real and what's fake. This way we can get the discriminator able to differentiate a poorly created image from that of the one which is slightly better one, and eventually it can generator can create a generator one. So of course the discriminator gets these all jumbled up, so it doesn't know upfront which ones are real and which ones are fake, but you do tell it as it learns when which ones are real and which ones are fake. So the discriminator improves over time because it receives more and more realistic images at each round of a generator, and it always remembers receives both real and fake images or jumbles up in a pile. So eventually it tries to develop a keener eye as the images get better. Also, the generator keeps on getting better based on the probabilistic loss provided by the discriminator on how much percentage the generator image resembles the original image. It keeps on improving and creates new fake images based on the discriminator inputs on the generator image. So this is basically a sample working of a GAN. So if you are very curious and if you want to find what are the people who are cater using GAN, you can just go to the sites. There are a lot of human like faces catered by using GAN, which are persons which are not present in the real world, but these are catered by the GANs. Okay, one of the main important factor of GAN is that GAN is very data intensive. Basically, deep learning is very data intensive, as you know. But for training GAN on unlimited data is difficult because data scarcity causes issues such as unstable training dynamics, reducing the fidelity of the generator image, and memorizing the training samples. So, what can we do to address these issues? There are a lot of new data augmentation techniques have been created to increase the data diversity and preventing GAN models from overfitting the training data. A lot of augmentations like rotating an image, scaling the image, cropping the image, left side, right side view, etc. are being done to address these issues. Okay, why do we need regularization? Regularization is an important factor in any machine learning or deep learning model, such that the model generalizes and it works well with the validating data when compared with the training data. So we need a model that is more generalized. So what we can do is to generalize in GAN, there are basically two important aspects to consider. Stabilizing the training to ensure that the convergence, such that the GAN converges in a proper and right manner, such that based on the discriminator input, it would be able to create new fake images that is resembling to the original input and mitigating the mode collapse issue. The mode collapse issue is one of the most important cases in problems in GANs where the discriminator is not able to differentiate the original and the fake, since it is basically the generator creating one sample of the same image repeatedly. So I looked into a paper on regularizing GAN with limited data, where the author described a new technique for regularizing GAN with limited data using the F divergence technique. F divergence is basically the probability of an probability difference between two events. So basically, probability of P and probability of Q, and the difference between those occurrence is basically an F divergence. It is a concave function, and at f of 1 it is basically 0. So as we are training new images and the generator creates new images that resemble the fake, so d of x is basically the real image, d of g of x is basically the fake image it is created. So these are the two equations, and we in the new regularization method, the author adds basically two anchors to track the discriminator predictions, which basically use exponential moving average variables. The anchors are used to compute the regularized discriminator loss to improve the generalized performance of the GAN models. So this is what I said. During the GAN training take, we can use exponential moving average called anchors to track the discriminator predictions. The anchors are then used to compute the regularized discriminator loss to improve the generalized performance of the GAN models. So the core idea is to regulate the discriminator prediction during the training phase. So LD and minimum of LD is equal to minus VD of lambda of RLC. RLC is the new regularization factor that we are creating here, which is proposed in the paper by the authors. So the RLC term would be able to regularize, which is basically an F divergence technique, which is a kind of an F divergence. Okay, why do we need a moving average? So following the predictions, the moving average reduces the variance across many batches. So instead of reducing only at a particular phase, if we reduces across many batches and stabilize the regularization term, then you'll be able to provide great results, similar to the momentum in machine learning, where we use the exponential moving average for moving up the hill. Similar to that, we can use here exponential moving average to regularize the GANs. Intuitively, As I said, the moving average stabilizes while the discriminator predictions gradually approaches the stationary point. So, what is this connections to the new F divergence techniques connection to the Lee-Kum divergence? The new regulation system that he has introduced by the authors is called the Lee-Kum divergence or the triangular discrimination. Was the new divergence, the new regularization technique, and the new divergence was applied to the WGAN model. The regularization method used in WGAN model was able to reduce the F divergence, which is basically LC divergence, so Lee-Kum divergence. So that's why they called it the Lee-Kum divergence. So using this technique, we can say that we can be able to train GANs with limited data, and it has a very close relationship with the F divergence used in the other GAN models. Even the Goodfellow proposed a lot of F divergence techniques to reduce the loss. Basically, he proposed JS divergence between row distribution. Similarly, the LS GAN paper formulated for reducing the seek square divergence, and E began approaches the total variance distance. So there were a lot of papers written to reduce different type of F divergence techniques. So on comparing the F divergence on WGAN, we were able to see that the new Lee-Kum divergence were able to provide less loss and was able to regularize properly with the training sample. So it's quite good. So we compare the results of the Lee-Kum divergence with the data sets on applying with the existing GAN models with the and applying the new regularized term. The authors were able to provide great results. As you guys can see, the FID score reduced drastically on these 3 evaluation runs, so it's quite good. Yeah, it is a comparison across various data sets and various state of the art, and it was able to perform very well. Also, these techniques, the new Lee-Kum technique was applied after data augmentation methods, and it provides even great regularization on top of it, and it was able to perform great. So you can apply data augmentation and then apply the Lee-Kum direction on top of it to improve the regularization even more effectively. So this is what the final output when when the authors were able to apply to the training. As you guys can see, with the less training data, it was able to regularize pretty well, and it was able to provide great results. So what I'm going to conclude here is the efficacy of the proposed method can be stated that the performance of the GAN model, particularly in the limited data, can be improved when it is used in conjunction with the data augmentation methods along to further improve the performance. As I said earlier, you can improve the performance of the existing GAN model by using the Lee-Kum regularization technique along with the you can also use it along with the data augmentation methods which are currently available right now. So that's all, folks. Thank you. Hope you